Welcome, folks. It is now June, early June, and the weather is almost like March weather right now in New York. All right, so glad to have everyone here. Glad to have everyone joining us virtually. So, our long-standing tradition, the very first thing we do for each meetup is ask, who is hiring? So, I know a few people here are hiring. I saw someone, Eric, just posted in the chat. So, Eric, you first, because you posted.
It's not my group, but
who cares?
My company. They're hiring for a remote data scientist doing a lot of machine learning. So if you know, like with PyTorch or ML ops kind of stuff, check out the Slack.
All right, so he's referring to, for people who didn't hear you, because I'm not sure if it picked you up, if you go to the nyhackr Slack, which you can find at nyhackr.org, and you go to the job postings channel, you'll see a job that Eric posted just like 10 minutes ago. So go in there, check out the job for a remote data scientist doing ML. Kevin, I know you're hiring.
Yeah, so we are hiring about 6 actuaries right now, a chief technology officer, and then soon there will be a couple of data scientist posts up.
All right.
At Arch Insurance.
Arch Insurance, 6 actuaries, a CTO, and soon-to-be data scientists.
Correct.
Remote or in office?
Depends on the spot.
Depends on the spot.
Yep.
All right.
You can go to the links that I posted in the Slack a month ago or 2 months ago.
Could you repost it by any chance?
I can.
Can you repost?
Yeah.
All right, great. Kevin's going to repost. So we have a job from Eric at Disney, a job from Kevin at Archer. Archer or Arch?
Arch.
Arch. Anyone else hiring? No one. All right, no one else hiring. That's a good few job opportunities, so everyone go to those sites and find it. And by the way, folks, if you're virtual and you have a job, post it in the job postings channel like everyone else just did. Let us know if you're hiring. Always like to get people jobs. All right, the most important part of the meetup, the pizza is from Percy's Pizza. I see the regulars know what to do. Pull out your phones. Everyone pull them out. Come on. Go to bit.ly/pizza poll. One word, pizza poll. And cast your vote on the 5-point scale of how you think the pizza is. And let us know. There's a grand tradition we have been running for many, many, many years, well over a decade, of getting a pizza from a different place and then having people rate it. So let us know how it is. And for you folks who are watching virtually, if you're not eating pizza, let us know what you're eating. If you are eating pizza, let us know. If you're not, let us know what you're eating. There's a few ways to communicate with us during the meetup. If you're watching the live stream on YouTube, which I guess you are since you're hearing this, go right in the chat on YouTube. Tell us what you're eating. Vikram, where are you in the world today? Let us know what you're eating. What, is he here? He's on. Vikram, tell us what you're eating. Also, though, if you don't want to comment in YouTube, go to that nyhackr Slack I mentioned. If you go to nyhackr.org, our website, you can find it. There is a channel called Monthly Meetup Chat. Let us know what you're eating in there. It'll be awesome.
He's eating an orange.
An orange. Very healthy, Vikram. I applaud you. Everyone, round of applause for Vikram for eating an orange. All right, and speaking of long traditions, we have a few of our original members here. Sorry, I'm going to say, Harlan, good to see you. Kaiser, good to see you. Like, Harlan might have been like at the first meetup ever. So he's an old timer here. He's been here with us a long time. Good to see you again. And I want to thank NYU and George, who is not here, for hosting us again in this lovely space on this beautiful park. So thank you very much, NYU Prism Center, for hosting us. Thank you, George. I think you're somewhere overseas right now, but thank you for taking care of this every month. And we're really appreciative of NYU. And if you want to learn more, go to nyu.edu, right? Or the Prism Center specifically. All right, July coming up. Bless you. Our July speakers, Kevin, going to be talking to us about spatial data and insurance. It's going to get more detailed than that, but you'll read the title. We'll post it in a few days. We're really excited for this talk. It'll be July 10th, I believe. Yep. All right, July 10th, come see Kevin talk about geospatial data science and insurance. All right, and then we'll announce the speaker in August later, but we also have our New York Data Science and AI Conference. It's our 2-day conference plus a day of workshops. We're really excited about this. This is the next iteration of the long-running New York R Conference. We have a great lineup of speakers. We're adding more speakers every week. So check the website for that. You can go to dataconf.ai to see who the new speakers are, what workshops we have. We're about to add another workshop in the next day or two. It's going to be a cool, building in an LLM chatbot into your Shiny apps. So that should be really cool. Come on in. If you want since you're a member of this meetup group, watching virtually, you're members too, you can get a discount to the conference using code NYHACKR for 20% off. So dataconf.ai, go there and use the code NYHACKR for 20% discount. And for the people in this room and the people currently watching on TV, on YouTube, on their phones, wherever, we are at the end of this meetup, in between the talk and the questions, we're going to give away 2 tickets. One to someone attending virtually, one to someone in this room. You have to be physically in the room to get it. Virtually, just have to be answering our emails. All right? So we'll give away tickets at the end of this. In our grand tradition, which Harlan remembers, we will be going to the bar afterwards. It's our grand tradition. We always go to the bar after the meetup to hang out and talk about the stuff we just learned or other stuff. If you don't drink, don't worry. Have water, have soda, have food, have whatever you want. Just come and hang out and have fun. Given the beautiful weather, we are going to be going to Vol Denis. Some of you know it, some of you don't. It is on, I think, West 3rd, right by 6th Avenue. It is a Belgian beer bar with a little outdoor space. So if anyone's watching virtually who wants to come to the bar but not to talk, come. Everyone in this room, come on down. It'll be a nice time to have a nice beer or non-beer as it may be. All right, with that, we covered the pizza poll, the jobs, the conference. Anything else I forgot? Anyone? Any have any announcements? All right, cool. With that, we will go to our speaker for this month. You can see the talk already here. LLMs and knowledge graphs is the future of data. So everyone, please welcome Alessandro.
Hello, everybody. Hi, nice to meet you guys. Well, I know some of you, and I'm glad some of the founding members came out for this talk. Hopefully, I will impress. I already let you down there. All right. I just want to introduce myself. And first off, thanks, Nicole, and thanks, Jared, for running this. It's an awesome one. I probably, out of all the meetups I go to, you get really good people who ask really good questions and are really dialed in. So hopefully you won't zone out. That's just more a reflection on me than you. So appreciate it. A little bit about me. Former Snowflake, former SurrealDB, which is a multi-model database. I'm really passionate about AI and data. I mean, everyone has to be passionate about AI because if you don't, you're under a rock and you're probably never going to get a job again. But that's a whole other story. And I know people are looking for hiring. That's probably really germane. And I'm really in this space of being an evangelist for these type of things. But I want to get into my journey of why I'm talking about graphs today, right? So knowledge graphs, at first, it was SurrealDB. A lot of people were really interested in using graphs with vector. Why? Well, a lot of people are using vector because that was a new renaissance of how you activate an LLM with RAG implementation. And now this graph thing came along, and I believe Microsoft first published this thing called GraphRag. And it actually is pretty effective. So when these things came around together, it created a new powerful paradigm of going after knowledge graphs and vector search to really enable AI to do a lot more better things. At the end of the day, the biggest challenge I had, and I'm only talking about LLMs in this context, I'm really going to talk about how we generate knowledge graphs, specifically because I needed to get knowledge graphs to demonstrate the power of this. How many people have worked with knowledge graphs here? See, this is the problem, right? We have a bunch of people, about 2 or 3 people raise their hands. How did you guys get your knowledge graphs? Was it a system that somebody actually keyed in information that was already in a knowledge graph format? Or did you have to generate these things from existing corpuses? The former? Both? A bit of both, right? But it's not like a turnkey. Someone thinks they're going to go buy Neo4j and have a knowledge graph tomorrow. It's not the case, Yeah, it's a little bit more tricky than that. And now, I just want to make sure that I'm sharing my journey, and hopefully this will resonate with you guys for some techniques that might be useful in your day-to-day. So, the problem. They're really, really important. It's really good to understand why these things are important. I'm going to sum this up. I'm going to make it quick. It's about information density. At the end of the day, if you can represent this data in a graph, it's very, very powerful because you're creating, if you had a whole book of knowledge, an entire encyclopedia, and you condense it down to a knowledge graph format, it is going to take that whole thing and reduce it by a huge margin. Now, that's great. It also allows you to do other things because 7 degrees of Kevin Bacon type approach, and you're going to see like iterations of things connected to other things that creates patterns that are very powerful, especially if you're an LLM. It's going to give you hints to things. It also allows you to do just things that are just quite frankly impossible. As a database guy, when I try to explain what a database is to a layman, I use Excel spreadsheets as the concept. It's pretty easy to understand columns and rows. It's almost impossible to tell somebody with Excel spreadsheets how to represent a knowledge graph. So I'm gonna lean on Neo for J, and like this is what they say a knowledge graph is. I think this is way too complicated. I think it's much easier than that. This is what a knowledge graph is for me. It's nodes and edges, right? Our friend Mr. Mackey here, he works at South Park Elementary, and he's friends with Chef. Now, the reason why graphs become powerful is obviously other people work at South Park Elementary, but other people are students at South Park Elementary. Chef is friends with other people. The actual edges themselves have properties. So when did he become friends with Chef? And did they ever have a falling out? Is he still friends with Chef, right? The nature of him working there. He's a teacher, or is he? Or is he just, a creepy guy? All these things matter because the edges of themselves have information. So here's some examples of some things I pulled out from corpuses. I'm just showing this just to show a really pretty picture of lots of nodes and edges. But the other thing is that you can see it's very hard to pull out like really strong representations like BlackRock and how they're connected to other hedge funds. How many finance people are in the office? Or in one? I know 2 or 3 other people. But this type of relationship becomes really powerful because if you understand how different firms or different entities are connected to each other, it's giving you a leg up. And if it's giving you a leg up and you're put in front of an LLM, you can imagine how powerful that becomes. So this is what I want to talk about today. We have lots of different types of data, and we want to get them in graph format. And the question is how? I have 3 general techniques I'm going to kind of discuss today. By the way, please, I'm going to poll you guys, but poll me. Ask me any questions along the way. I'm not going to, jump down on anyone's throat. The first trick is just using LLMs. So the first trick is prompt engineering to a certain degree. It's not too complicated. It works. You're basically going to have to, and I'll go through my tips for what this looks like. But the first part is be specific. You want to say like, hey, I want these entities. I want these things to be extracted. I want you, specifically to tell me, what you want out of there. You want to basically describe the database to the actual LLM at the end of the day. And next step is provide examples. Oh, I should also say, make sure you're giving it the steps in order. So don't say, just give me the graph. Make sure you say, pull out the entities first. Once you have all the entities, then find out how they're related. It's important that you do that, I should mention, because sometimes you end up with like connections that go nowhere, et cetera, and you want to be very thorough, that it's not creating hallucinatory craziness. And the other way you do that is make sure you provide lots of examples. So in this example, this is pulling out arbitrary text, and then we're putting down some descriptions of the actual entities and how we would say we want them to be related. In this output, you could also say like spit it out as JSON, as a CSV, whatever you want. In this case, I'm jumping through a few steps because in this example, I actually execute this. This is syntactically correct. The other really important thing here in both of these, if you look, there's this little end delimiter. The delimiters are really important for a few reasons. One, if you want to make sure the thing actually finished. If you're using APIs, sometimes you'll get an error that the thing stopped before it actually spit out all the tokens. However, another good way to do it is you just look at the output and make sure your delimiter is at the end. It's a little cool hack. The other thing you should also consider when you're looking at this is that you're probably going to do this in a loop. And I'll explain that in a little bit. So delimiters account for a lot. Next thing is you're going to ask your LLM to check its work. Did you do a good job? If you're a human, you might say yes. The LLMs are pretty honest when it comes to this. And you can put a lot of information even in the question of what you think definition of done is here. And if it didn't, iterate again. And you're going to be able to do this multiple times. Obviously, you're not wanting it to go forever. Put a stop to it in a sensible way. So this summary of this is you're going to define your blueprint, like what the order of operations are, exactly what you want. You're going to be very specific about what's going on. Give examples, and then iterate, iterate, iterate. And at the end of the day, make sure that you're giving the correct syntax. So, you'll be surprised. This thing actually works. They're very powerful now. You're going to get real code coming out, and if you're doing it the right way. Cool. Next step, NLP. In this example, I'm using Spacey. So this trick is basically going through and first finding all the just entities, and there's no other ground truth to this. So Spacey is pretty good at doing this. It'll pull people out. It's not perfect. Nothing's perfect, and you can always get better and better in this. The only trick I do here is basically once I pull out all the people, then I use fuzzy wuzzy to kind of mash the similar names together so I don't get a lot of misspellings of names. Pretty simple. This is a really good way to get good ground truth for entities that you're just kind of unsupervised, just pulling out data. Another example is if you have ground truth. So in this case, I know all the public company names, right? I know JP Morgan Chase, I know Citadel, I know Disney. Those are companies and words that I actually know. So I'm going to pull that list through, and now I'm going to create a nice little index so I can always look up those things really quickly. That's important, so you can go through a large corpus quickly. But now when I'm looking at these canonical entities, I'm going to do two things. One, if I find a match, great, my job's done. I found it. Yay. So the Spacey's actually pulled out the entity. In this case, it was an org. And it said, OK, is that entity in our index? Yes, great. Now I have it. If no, now I'm going to have to get a little more clever. I'm going to use a bit of fuzzy matching. And now I'm going to go through and find out of my list of all those indexed companies which one it's closest to. Pretty simple, very powerful. And it's much faster than the first technique that we talked about. So if you use an LLM to do this stuff on a relatively small corpus that would actually fit in your context window, I mean, if you're using one of the smaller models, the inference time is still going to be like 30 seconds, right? It's not ideal. If you have 1 million documents, good luck. So this will be faster, not super fast. And by the way, that was just the entities. I should mention, we also want to pull out the actual relationships. This is how it works. Basically, if you've gone through all of your entities, and this is very similar. So remember, we asked the LLM, find the entities first, and then find the relationships. And you can see why. In actual code, you're going to want to do something similar. So I have all my entities, and I'm going to go through the entity list twice, basically. And the whole trick here is that for each entity, I'm going to see what sentences are matched. And within those sentences, then I'm going to pull out the actual verb, which is still just using Spacey stuff, and the verb that's actually connecting them. I'm going to put in metadata alongside that the actual edge. And the last thing I'm doing is actually calculating a confidence using this. And a confidence here is pretty much just the number of references we had to it. You can probably think of other things that you might do depending on your corpus. Maybe there's other information that in the corpus that would also be applicable. But this is a very simple way of saying, like, hey, if I found 10 sentences that connected these two things, I'm pretty confident these things are connected. And then last bit, make sure you normalize. If you don't normalize, it's not going to be useful to your LLM. So summary here, we want to take out the entities first. If you have a ground truth, if you have a master list of any of these types of entities, you're going to use fuzzy matching either to coalesce a list and get lots of sprawling entities to match to themselves, or you're going to go against your master list. After that, you're going to extract your relationships, and then you can pull out your verbs in confidence, and then normalize the confidence. Make sense? Cool. So 3. Now this one's a little bit interesting, and I'm going to say it's a bit of a hack, but it actually works, and I'll explain that in a little bit later. So my first approach was like, what I'm going to use search extraction. By search, I'm specifically talking about full text search and vector search in database. Why? It's fast. So my first go at this was to say like, okay, so I have, and in this case this was ADV filings on this example. This is my process for inserting a firm. The first thing is I want to insert a firm. I'm going to see if it's matching an existing firm. If it's a known firm, great. I'm going to insert the relationship. I should say, I've already inserted all the master list of firms that I know. So this is coming through an entity that it's not exactly known. It's in one of the sections. It's kind of like a table within a listing. And if it's a filing that already came through and I already have an exact match for it, great. If it's not, I'm gonna have to insert that new firm and then insert the relationship. The problem with this is that if you're looking, and this is relatively structured data, there's lots of real noise in the actual firm names. So you're going to have, D. Shaw spelled 20 different ways with periods and commas and LLCs and subsidiaries and, Europe, whatever. It's not fun. So this was the nightmare. I kind of jumped to it, but this is a whole problem. And the other thing is we have these implicit relationships that are buried and missing. It was not doing a very good job. So when I wanted to use that graph that was generating in a very simplistic way for my purposes, I wasn't getting very good results. Even just displaying it was like displaying garbage. Like it would be very small, not very dense connections. It was just stuff sticking out in the ether. Not fun. So what did I do? I wanted to do a little bit more refining using this, so I started using full text search to try to do these matches. Didn't work very well, mostly because once you actually strip out DE, it's going to match all kinds of words. It doesn't really work very well. What actually did work pretty well, surprisingly enough, and this works specifically for names, start with. So if you're using any kind of database or any kind of the start with function, I'm using however you want to use it. It's actually pretty darn good. The only problem is that it's really slow because you can't index on starts with. Full text search kind of does with edge n-grams, but even edge n-grams are not great because it's going to look through all the tokens. So what did I do? I did another few things here. I came up with a notion of cleaning these strings, so pulling out a lot of this extraneous data that would hamper matching. Made sure that we, did a bunch of stuff with revisiting all the searching and all that. At the end of the day, the simple database stuff, it just didn't work. And any type of starts with that was like in memory outside of the database was too slow. So this was the kind of clever thing that I started doing. I had a thought. Well, what are embeddings? Everyone's familiar with embeddings here, I assume? Yeah, all right. So generally speaking, we think of embeddings as creating a vector representation of a concept such that words or binaries or whatever can be closely put together because they're related to each other. That's what they're originally kind of created for. However, put that right at the end, right? This is not the meaning we're looking for here. We're looking for strings that should be the same meaning, but because they're the same thing. But they're not the same meaning. And this is why I call this kind of a hack. So if you look at the actual list of all the names that are coming out, and this is basically what I did. I took all the names that were extracted, and I said, okay, spit them out in a file, and let's take a look at them. And that's what you look at. So I'm picking on D. Shaw, but you can see all the different ways that they're listed. What can we do with that? Let's train a fast text model. How many people are familiar with fast text? Okay, so fast text is a word embedding model Basically, it's going to use the context. Traditionally, what you would use these things for, is if you have corpuses of knowledge and you have lots of paragraphs and sentences and things like that, it's going to pull out all the words. There's some other things going on here, but fundamentally, it takes all those words out and it spits out for all the words that it finds, depending upon frequencies, and I'll go through some of these important parameters here. It will create a vector that represents that word, and traditionally, in a semantic way, if you're indexing, let's say, recipes, lemon and lime will have vectors that are very close to each other. Meat and fish will have vectors that are close-ish to each other, but beef and lamb will be very close to each other, if that makes sense. And when you use these, traditionally you would take the tokens of a sentence and you would break them up, and then when you basically average them up together, you create sentences and you can compare sentences in the same way. That's what you would normally be looking at. Just to highlight some of the parameters here, the things that I did a little bit different, and if you remember the D. Shaw example, I pick on that one very specifically. In a lot of firm names, you have two initials. JP Morgan, D. Shaw, 2 is really kind of the critical thing. So I basically built a function in my cleansing that would take anything that was like a single letter after removing punctuation next to another single letter in punctuation and make sure that they're together. So I'd have this magical number 2. And that's where this min of the minimum length of characters of the n-grams would be 2. The n-grams is I'll talk about a little bit in a second. And the other little trick here is if you look, there should be min count. Yeah, I'm trying to read on the screen. Min count's at the bottom. And I'm saying I want every word that you find in this corpus. Why? Because I'm using this as an index to look up words when I'm actually going to do comparison. So if a firm was actually in there, it never came up, I'm not going to find any match if I didn't take every word out. I'm being very greedy here. This is not something you would do probably if you're actually going to use this for semantic understanding of a corpus. It won't be very effective. Now, the other thing, I didn't actually put a slide on this, but this is on the n-gram part. The trick here is, as I mentioned, I'm getting those 2-letter characters there. And I'm also doing the strategic pruning. But I should also mention I'm actually sorting by alphabetic letter. So I'm jumping around a bit. Remember I said starts with works really well? So anyone have an idea why alphabetically listed, sorted these? It's the starts with, right? So if all these things are close to each other, and we know that these algorithms like to put vector weights that are going to be very similar to each other when they're close to each other, this is the hack. I've made sure that all the similar firms are close to each other because I'm taking advantage of alphabetical sorting. So now I'm seeing that D. Shaw is going to be very close to D. Shaw, but not close to Deutsche Bank because of the sorting. And now I'm getting these nice vector representations that I can actually see that something like D. Shaw Limited UK blah, blah, blah is going to be close to D. Shaw Corporate and not close to Deutsche Bank. If you're using standard string manipulation like Levenstein, you're going to actually not do that because it's just looking at all the letters in the word. So we have a very, very powerful way to go after this now. And I also did a bit of, let's call this metadata hybrid approach. So if you think about it, I had this notion that in the information I also had alongside these words, well, I also know some other things about them. So if I know that 2 of these firms are within the same state or city, I can actually up the score a little bit and then further refine. So we're going to use the vector search, basically get, say, the top 10 results that are close. But then within those 10 results, let's say there's a bunch of D. Shaws, and I want to match on the 2 D. Shaws that are actually in Europe, I can do that as well and get very precise. So once you put this all together, I'm basically going through this. I'm matching the firms, as I said, and then I'm also putting that score, and then I should say this little, I I have no cursor on this thing on the screen. Let me see if I can do that. But this little guy here, in this context, this is doing the 10 nearest neighbors in an HSNW, which is a vector index. Sorry, don't make me actually say what HSNW is out loud. And it's basically saying, hey, get me the 10 closest ones using that technique of vector similarity. And then I want you to sort by the score, and then I'm going to return the best one. So the hybrid approach. What are we doing here? We're going to basically say, let's use the vectors to find them, score the strings, and it's going to work. So the workflow is, again, clean. Build your actual fast text model, then perform the vector search, calculate the weighted strings, and then you have your answer. And this is what that new little workflow looks like. So before, we didn't have this. So when I'm ingesting, I'm going to extract. Sorry, I can't even read my thing. Extract and clean the data, create the fast tracks, blah, blah, blah. And I just kind of went through this. And now you have really clean graphs at the end. So I went through a lot. I went through this pretty quickly. I know we have beer coming later. That being said, I'm going to make sure to get through all this. Pause for any questions before I move on. Cool? All right. So just to sum up these different techniques, and I didn't go into what the pros and cons are. The technique number one, which is just using LLMs to generate graphs. This is the one that's actually, I believe, in Microsoft's original GraphRag implementation. And this is they do a lot more sophisticated things, and you can go deep there, but it's going to be expensive. You also still have hallucinations to deal with. It's a black box. You know all the problems of using LLMs, but if you're using an LLM to basically generate data that you're going to feed to an LLM, you can see what the challenges might be. It's a really good way to start, though. I would say this is really powerful. You should probably take a look at this, especially if you have to get like an MVP or something out the door quickly. It's a great way to start. Next up, NLP, right? So this was really powerful. It's faster than using the LLMs, but you have to write a bunch of code. You have to really know your corpus pretty darn well. You're going to have to know exactly what the type of entities are. You're going to have to really go at this. But it's a nice hybrid approach because you don't even necessarily need to have a version of truth to say like, here's my master data. But if you do, it's going to be a lot more useful. And the last thing, but I should say, you do still have some challenges because, these things are not also perfect. It's still machine learning libraries, and they can make mistakes, and you have to do a lot of fine tuning of just your own code. The last part, as I mentioned, the search extraction. So using combinations of full text search and actual metadata and using kind of a hacky way to go after vector embeddings to pull out this data, it's really powerful. But yeah, you got to start with kind of at least some form of structured data. It's not going to work just like an arbitrary corpus of data. It's going to be very good for doing like string matching and stuff like that. And remember, a lot of your data out there really already has lots of basically structure that is a vector. That is a graph in there. It's just your problem is it's not stored as that. So I would say this is probably your best bang for your buck when you're trying to generate new connections between data. And this is my little matrix for how I like to explain it. And now that we have a few techniques, we can have some pretty things. So we can generate these nice little relationships. So going back to D. Shaw, we can see like how much money Fidelity or other hedge funds are actually sharing with each other. So this is all publicly available data, and again, I can't see very well, but yeah. So $583 million is being, looks like, Davy Portfolios. I've never heard of that company, but someone might be interested in $583 million. It's something that's publicly available and probably not very easily accessible unless you really dig through these things. So it proves its value right there. So I can go to a demo now, or we can pause for questions.
You gave examples of basically cleaning entities
Yeah.
Is there a similar process for relationships?
So it depends upon the technique. So, all right, let me go back. So, maybe I won't do all, that's pretty far. So when you look at the LLM approach, the extraction process there is whatever you kind of decide. Be creative. I mean, you could say like, hey, I want you to pull out, how these things are related, and I specifically want you to give a score of how strong your relationships are, however you see fit, or you could say like, I want you to do it based upon the number of times they're mentioned with each other. You can basically create the rules and not have it encoded like in a real way. It's prompt engineering. In the spacey NLP approach, I should also mention the other thing I do here that makes it really explainable, more so than there, is I tend to take the actual context when the relationships are actually being detected. So if you remember that finding the two entities in that nested loop, it's actually saying, hey, what's the blobs of text where these two entities were actually mentioned with each other? That's the first trick. So we have all the blobs and we're saying, hey, in these blobs where you mentioned this one and this one, let me see that blob. And then we're taking that and saying, hey, in that blob, try to find me the verb that makes sense that are connecting them. And then you store that actual context. So you can actually use that for doing vector search for other purposes, like for doing a RAG.
So you might clean that word.
You could actually take that in theory and also say, like, I want to pull out specific other meta information that might be in there. So if we're going to stick with financial services data, you could say, like, hey, I want to always pull out anything if the number next to the word revenue, if revenue is mentioned, or you can figure something out. If it's in a recipe, you'd say like, okay, if the verb is, you know what the verb is. If there's anything mentioning amount, pull that out, right? Like the number next to amount. I'm making this up on the fly, but you can imagine how you can do that. The last one, since it's structured data, you have the metadata there already. Right? So in that use case, you're really just using this to kind of do the logic of, hey, I know I have lots of messy names and lots of messy entities. The structure of the graph that would normally come out all messed up is you would have these really sparse graphs because you would have these connections between entities that would just die. But this entity is likely already represented in some other thing. Or even if it's not, once you insert this once, and some other company is also mentioning that you want to make those, so you have, that 6 degrees of Kevin Bacon, not, everyone only worked in one movie with a guy who spelt his name wrong that one time and never sees it again, right? Like that's what you're trying to solve for. Does that kind of answer your question? Yeah. Cool.
So because I've been living under a rock, I have 2 very basic questions to ask. Forgive me, I still haven't been able to figure out. When people speak of knowledge graph, they basically just mean a graph database, right?
Yes.
Okay.
The knowledge graph is the actual data. The graph database is where you store it.
Okay. And what is the basic point of departure for when a graph database becomes more useful than a genuinely well-curated relational database?
So the way,
Just to use that dirty word that you haven't been mentioning, relational database.
oh yeah, look, I'm an old school relational database guy. Like that's my bread and butter. To be fair, it's a simple thing. It's how many joins do you need to do, and to get to that answer, right? Like that's the simplest. But then you have other kind of more specialized questions like shortest path. So if you say like, hey, I want to know how I'm connected to Kevin Bacon, get me the shortest path to that. That's a very tricky question in a relational database, right? So there's lots of little niche reasons why to do them. I'm not even going into like graph analysis.
That's an excellent answer.
All right, I'm gonna, yeah.
So for the first technique regarding LLMs, so the example that you gave was about a specific type of relationship that you wanted to extract in a closed world hypothesis.
Yes.
So, do you have any suggestions for what to do for an open world? So if you don't know in advance what the type of relationship you want to extract would be?
Someone actually came up with that last time we had this conversation. I intend to do an example that's just kind of like let the LLM kind of hallucinate, but like be very specific on the output and see what you get. That's something I think would be actually a really interesting thing to check out. I think the challenge is honestly, but in a real world scenario, you're building these graphs to kind of ground the LLMs if that's your purpose. I think that's going to be fun just to see what comes out of that. Like, hey, just tell me everything that's in here and how everything is related to everything else, and just make sure you spit it out as JSON. And I'm sure you'll get some really powerful, interesting information, but it's probably not going to be very useful to then use further down the stream when you're like actually trying to solve something, like ask a question of that via an LLM.
There'd have to be a lot of alignments and a lot of verification.
Yeah, yeah. I mean, maybe there's a way to, if you're thinking about just with a quantitative thing, like, only pull out things that are mentioned like over 100 times. Or I don't know, but yeah, I think it's something to play with. I think would be really fun.
Absolutely. Thank you.
All right, let's see. I gotta switch some stuff around here. All right, now we're mirroring. All right, let me. Okay, so can everyone see this, or do I have to make it bigger? Is that legible? I don't think so, right? Is that better? Thumbs up? All right, so this is us using the LLM approach. It's just my imports. So just walk you through here. Completion delimiter, as I mentioned, is important. In this case, I should say what the actual corpus is. This is just a little novella. It is the same one that Microsoft uses in their demo. And it's pretty big. It's a little science fiction story that's about some guys who are soldiers or something, and then they get like a signal from outer space. Or I never actually read it, but if you want to read it, I'm pretty sure it's horrible. I don't want this to go forever, so I'm putting max retries, and I'm specifically pulling out the person and the place, and the thing I'm describing as a relation I'm not very creative here, related to. And let's go through this. Did it doop. And this is how we call that thing in a loop. So if we're calling the LLM, we always want to make sure that it ends with the completion delimiter. So that's the trick. We'll call this in a loop up to 10 times, which is going to use the prompt, which is over here. These are the prompts. This is the actual graph extraction prompt. Here are the steps I'm telling it to go through. Let's make sure your entities are defined, blah, blah, blah. And then return the output. Completion delimiter, yay. And we give some examples. As I mentioned, give lots of examples if you can. Here's a whole bunch. And not that it's all that important, but this SQL syntax is actually syntactically correct in this particular database. You can imagine it would be, instead of create, you'd have insert, et cetera, et cetera. And I'm not a Cypher guy, but if you're using Neo4j, you'd have a different syntax than this. But you could spit this out. You could also say, like, hey, just spit out as JSON. Here's some examples. And while I'm here, because I don't want to go back and forth, this is the continue prompt. I have to say, though, prompt engineering-wise, it's very good to make things big and bold and capitalized when you like just. It's surprising how silly sometimes this stuff works if you just say please. So, even though I believe some of the people out there saying please is redundant, you're wasting our money by saying please. It actually does give you different results. So I'm not listening to you, Sam Altman. And also, this is the prompt for, just say yes or no. This stuff will work, and like all demos, maybe it won't. This is me I'm using Gemini for this, Gemini Flash, And in this case, Flash, by the way, just one thing about Flash I do really like, it has the ability for their APIs, if you have a file that you want to reference, you don't actually have to cram the file in the actual prompt. You can actually upload it offline and keep referring to it. Just a nice little feature. And now we uploaded the file. Here's an example of here we go. So it's spitting this out. This is an example of us calling that first prompt once, and here we go. So we're actually getting syntactically correct stuff, and this is the actual response that becomes raw. And now we can write a little function here that we're going to generate the content until complete, and we're going to take all the parts that were the text, and we're just going to basically write it to a file so we can take a look at it, what comes out. And as I mentioned, we're going to go across this at least up till the max because we don't want to be here all day. And if you look, we're going to ask the question in a loop if there are any more relations. And any more relations, we're going to say if it's yes or no. And if there's more, then we ask that continuation prompt in a loop. And we should get some stuff out. And while it's doing that, this is why I said LLMs are probably not the best way to do graph extraction. This is not a very big corpus. And you can see I'm going to have to make up silly jokes, dad jokes or something while it's doing this. It's continuing. Let's see. Where did the pencil go for vacation? There you go. You have a kid too?
No, I saw it.
All right, cool. Now let's see what it actually generated here. So yeah, I will tell you this is likely to be syntactically correct, but we can be sure to make sure that we insert it. So this database is actually up and running, and I don't have to run that. And it spit it out. So it actually inserted that, and now just to confirm what we're seeing, we don't have to go in much detail, but df1 is the sample query, and the sample query is here. I'm just selecting the ID description. This little operator is saying like traverse through the graph, this is the relational table, the edge table, and pull out this metadata that I put in there, and it does return that. So, and we can take a look at what this looks like in a tabular form. So this person, Alex Mercer, is related to these other people, and that's the strengths. And here's some description of the actual relationship they have. Here's a nice little representation as a graph. Looks like New Mexico ended up stranded over there. I don't know why. I'm sure if we ran it a few times, it's an LLM. We'll get a different answer. Yay. Consistency, not great. But yeah, you're getting a general sense of how this stuff works. And now you can actually use this. Now, you can do this. I can even show you. So let's say DeepSeek here. I want to be mindful of time. OK, actually, that's how you graph. We don't need to do an actual RAG. Let me show you some really interesting examples here. Let me just switch over here. OK, here we go. So this is that ADB filing example. So if I go here, now I can, in this case, I'm going to search. This is one of the graphs that was extracted. And this is doing a semantic search for hedge funds. So why is that cool? Generally saying, I'm searching for hedge funds. Now, if you look at what I actually stored, there was no actual flag that said hedge fund when I'm typing. Or this was the actual hedge fund. But when I'm jumping around here. I actually know that's a hedge fund. But if I want to do here, let's say Shaw. this will be actually showing where D Shaw is connected to hedge funds in real time. And if we take a look at that one's going to be a small one. Let's take a look at this guy. So we can see the graph of this actual, my UX is awful. Please don't ever hire me as a UX designer, because this is what happens. And all right. It's probably easier if I just show you this. So we can see how they're connected to things. Oh, and by the way, in ADV filings, if you don't know, there's a section that has to list all the custodians. And if you're ever curious of which financial institution uses Amazon versus Microsoft or Snowflake, you can actually find it there. Just a little interesting thing, or Iron Mountain. But yeah, you can also see how they're connected to other private firms. So this is all subsidiaries. So that was that Davy portfolios thing that we saw before. So we can click on Davy and take a look. So this is custodian for here. And obviously I didn't format this, but that is that very big number of 583. That's a pretty big chunk of change. Yeah?
I want to clarify what your problem statement is relating to kind of the whole thing about multiple entities meaning the same thing. I think you're trying to clean things up, right?
Yeah.
So is the goal there to retain all these nodes and sort of somehow make it identical, but it's still there? Are you trying to replace all the different names of like one chosen name, and if there's only one node left in the router besides that one?
Yeah, I made this, I don't even, all right. Sorry, I'm trying to, let me uncheck this a little bit and then see what comes out. So the challenge here, actually, let me just clear all this out. So it's probably easier if I just show you everything. So this is after it's being cleansed, right? Now, if you take a look at underneath the covers of how a lot of these things are, you'd end up with, it's very hard for me to get in here. And actually, this is why it's not so impressive either. I was only showing 100. This is what you actually have. So, and I know this is graphics running on this local computer, so I might have to. If I put in a round of at least, this is still going to be very big. Yeah. So this is why it becomes a problem when you have that many entities and you have so many different random spellings of stuff. You end up with these connections that should be there, but you can't actually find them. So in a graph, it becomes very sparsely populated. So you would end up with, D Shaw being connected. Its strongest graph relationships would be to like all of its subsidiaries, because you would have that and you'd have all these things and all the multiple different ways that you were spelling it. But then those subsidiaries, they're not actually doing filings of their own, for instance. So you never get those hop-on effects that are very easily to connect the dots to. Or more importantly, that's even when you have that D Shaw to start with, like the corporate master. A lot of these firms are like listing other firms that are also not like a master list of a filer. So you would have, like, I don't even remember, Davy, whatever that firm was, and it would have multiple different ways that people were entering that. And unless you can actually connect these as actually being the same entity in some way, you get these sparse graphs. Does that make sense?
I mean, it seems like, because then if we're trying to disaggregate it, so we just make it one entity, then we have one problem is like, what name do you give this entity then? Could it be under many different names?
Yeah.
And then the other one is how do you deal with a living database where there will be documents that comes in, where it could be any one of these many different names that you somehow now still need to, because that would be a graph that the one name as opposed to the 100
Well, think of this as like just deduping for the, like, not the metadata of the deduping is you can keep as well. So all these things are also associated in the edges with specific conditions, right? So just because, let's say you mislabel something, there was another thing that was in DE Shaw and you somehow, it was supposed to be DE some other, like she, I don't know, and you had some, and you calling it DE Shaw. Is that the concern that you're bringing up, or are you more about like why did you have to consolidate them because you'd have all these nodes, right?
Well, I mean, I'm trying. I guess I'm just trying to clarify whether all the different names are retained, and then we have some relationship that kind of just bound them together, or we try to have unique nodes for each entity.
So the purpose of this is, all right, so think of it this way. The graph is not trying to find, like you don't have like one point that represents the company and that's it. The points are the nodes, but the edges become important because you're going to have those nodes multiple times in your graph. And they're going to have multiple connections to other nodes in that graph. And the number of connections and the metadata in that connection is what is actually really important. So it's like, you know, think of it like as, you know, when you go to a store, right? You as an individual have lots of orders, right? It's not useful if every time you ordered something, you had a different ID every time you ordered something, because you wouldn't be able to ever discern like what's the pattern of me ordering stuff and, you know, what should I order the next time. So that's kind of what this is solving for at a more simplistic level. But why in graphs becomes really important is if you have too many nodes relative to the edges, you have a very sparse graph, and that's not very meaningful. So if you only have two entities that are connected, and you have 1,000,000 two entities that are connected with like one line, that's useless. That might as well be in a traditional database and, you know, or a Word document. Like that's what you end up with. Does that kind of make sense?
Yeah, I mean, I think it helps me kind of think about the things where you're answering.
Hey, no worries. I had to kill that because it was destroying my computer, putting like, what, 100,000. All right. But are we good with time? Any other questions?
Like 2 more.
2 more? All right. Other questions while I have this blank screen on?
Oh, yeah, no, good, bro, thank you. All right, let's see. All right, I'm just going to read it verbatim.
Sure.
Most graphs are heterogeneous, meaning no degree is exponentially distributed. That is, there will be a handful of companies with a lot of relationships, and there will be a lot of companies with few. Is there a computationally quick way to build graphs in such cases? It appears the algorithm shown, I'm not sure how long ago this was, shown as quadratic in the number of companies, which could be computationally suboptimal.
Yeah, I mean, you probably can optimize that. This is just me getting some techniques out. At the end of the day, if you're doing this and you're doing this at scale, yeah, there's probably other ways to go after order of operations. I mean, you should always do that if you're doing engineering, but I'm building demos and just showing the art of the possible. But
it's left to the reader as an exercise.
yeah, I would say this. Also, these Git repos are totally accessible. Please just like pull it down and make my code better so I can be selfish.
One more. We've done that.
All right,
Thank
cool.
you very much.
All right, so first, remember, next month, Kevin is giving a talk about spatial data science and insurance. And in August, we have our conference coming up, the New York Data Science and AI Conference. And with that, I think that's everything. Remember, if you're looking for a job, go to job postings. If you're trying to hire someone, go to job postings. Works for both directions. And everyone who's here or even virtually wants to go to the bar, Vol Denis. I think it's West 3rd and 6th, but just go to Google Maps. It's VOL space DE, or it might be DU, space NUIT. Vol Denis, Belgian beer bar, nice outdoor space. I'll see you folks there. If you're not there, I'll see you next month. Everyone have a great night. Thank you.